while the boy is trying to share his screen, this past week, last weekend, we started the class and we did a review of measures of central tendency. And we also we did a very quick introduction to like visualization and some of the challenges that you might anticipate with visualization, and how to select the best way to present your data. Today we'll look at measures of spread or measures of dispersion. But before today's class, during the week, we had 3 lab sessions, 3 lab sessions, and we had very good attendance. That's great. And the classes were well attended. The participation was great. It was highly engaging. So that's very encouraging. I think most of the classes were able to go through the material. So this morning's class was not able to completely, this afternoon, depending on where you are, was not able to completely go through the material. So we will try to release a video early on, so that you people can be able to review. And apart from releasing the video early, the other thing that we'll do is see if we can organize a makeup class for people who couldn't attend this morning. So look out for email. And if you think that you still need to catch up as well, you might benefit from that class. But I think it'll be good to, first of all, try to watch the video of the classes that we do release so that, yeah. So Ebua, let me know when this.
I am ready. Can everyone see my screen or?
Yes, we can see your screen. Okay.
Okay. So let's see. My video is coming on. It does not come on. That's fine. So why don't we do ground rules? So if you have a question, please type in your question in the chat and Dr. Abioye will try to respond to them. Dr. Abioye will also reach out to me and maybe interrupt the session if there is a serious question that needs to be attended to.
Sorry, before you go, I just want to say that we shared the slides yesterday in the email. As much as possible, we try to share the slides at least 24 hours before the class starts. So if you don't find it, if you haven't received it, please check your email carefully and also check your spam. Okay, sometimes, if you bulk email to people, then it might go to spam. So please check your email, check your spam, and you should find it. Yeah, I think that's the key thing that I wanted to point out as far as the material is concerned. Yeah, please go ahead, Ebua.
Can you hear me?
I can hear you okay.
Okay, sorry. Great. So the second ground rule, or I wanted to say something about the first. If you are absolutely lost and you really need some clarification, feel free to unmute yourself and ask a question.
Sorry, as far as unmuting is concerned, Ebua, I think people will not be able to unmute by themselves because this is webinar style. And what they will need to do is raise their hands and then we can call them up.
Okay, so if you really need to, send your message in all caps and Ibrahim will respond to you. So why don't we, let's see, we're 1 minute, one more ground rule. So this is, because this is webinar, it's not going, I won't be able to call on people. So let's abandon that. Okay, let's move right into today's session. And Dr. Abioye, please let me know how I'm doing on time, so that I'm not carried away explaining one when I should be moving to the next. So what are measures of spread or measures of dispersion? Today, I'm going to show you, or we're going to show you what we mean. And what I'm going to try to do is explain why these things are important. Very high level. And I'm going to tell you this very high level, even if you don't understand it now. Why? Because what you hear now in future, when you get better and better at statistics and epidemiology, what you've heard in the past will make a lot of sense and will guide you forward. in statistical analysis, it is really, and Dr. Ibrahim, you can add or you can correct me, it is your error terms. It is it's your error terms that actually help you know if you are doing the right thing. Can you imagine? It is not necessarily the predictability of your outcomes. It is how the errors behave that lets you know whether your analysis is statistically significant or not. And as we go along, you're going to see a term called standard error of the mean, the error of the mean. And that's what helps you know statistical significance. And this is one of the reasons why measuring spread or dispersion is useful. Again, you might not understand what I just said, but open your ears, and as you go further, you will likely find out that this is not only true, but it would help you understand the basis and principles for statistical analysis. Okay, so let's go in. I can see a very dark box.
So I'm not sure why it kicked everyone out.
And okay. Okay, so I'm going to continue where I believe I left off, and please let me know if I stop talking or if you stopped hearing me long before this. Okay, so this is the very beginning of the slide, so you've not missed anything apart from me rambling. So here's why measures of dispersion are important. If you all can see my screen, I want you to look at these numbers, this first set of numbers, starting from -10 to 20. Just take a second to look at them and look at what their mean is. The mean is 5. You know, it's written here, if you can see my cursor. But also look at these sets of numbers as well. And you would see that the second set of numbers, 2, 3, 7, 8, and 5, are more tightly bound together than -10 all the way to 20. If you remember your mathematics on a number line, the number line for the first set of numbers is much wider than the number line for the second set of numbers. But you can see that this measure of central tendency, which you all studied last week, is the same. So if you say, if you were arguing with your friend, for example, and you say, you know, what is the mean income in, let's take Sierra Leone or India or Nigeria. And someone will say, well, the mean income in Sierra Leone is, I don't know, $40,000 a year or $50,000. That shows that the Sierra Leoneans are doing great, you know, and everyone's clapping and saying, yes, excellent, great use of data. But another person will come up and say, well, maybe the mean income in Sierra Leone is 45,000 because Mark Zuckerberg, Jeff Bezos, and Elon Musk moved there. And so they pulled the mean to the right. When you look at the distribution, however, you're going to see a lot of people are on $100 per year, and a few people are on hundreds of millions of dollars on the right, and that's what makes the mean pool so great. You're beginning to see why a measure of dispersion is important in addition to your measure of central tendency. The spread helps you, knowing the spread helps you to make better meaning of your measure of central tendency. The second point on this slide, so the first point talks about the mean. So many of you might say, yes, the mean is subject to outliers. We already know that. And so you want to use the median. But look at the first set of numbers here, starting from -1,000 all the way to +1,000. The median for this set of numbers is 3. So someone's going to come out and say, well, the median income, maybe we should not use the mean, maybe we should use the median. The median income is $30,000 in Lagos, Nigeria. That means 50% of, and this is a refresher in case you forgot the meaning of the median, 50% of the population in Lagos, is doing very great. And remember that it's not just 50% lower, 50% of the population has an income greater than 30,000. So and everyone claps and says, great use of data. But look at the second set of numbers between 1 and 5. The median is also 3. So even though the mean is subject to outliers and the median is better, the median is not necessarily the best until you understand what the spread is. Okay, so the third point here is what I said at the beginning. The spread helps you understand statistical significance between two or more populations. And you see, someone put more on that later. I'm not sure who it was, but that's a good way to capture this. Let's move to the next slide. Okay, so when you're trying to understand spread, so let me say what I just said before so I can link it here. When you're trying to understand spread, you're looking at how dispersed the data is across what we call a distribution. And we're going to talk about a distribution very soon. Okay, so when you're talking about range, you know, range just means what is the maximum minus the minimum. If this was not a webinar style, I would have called someone and said, what is the range of this set of numbers from -1,000 to +1,000? And as a refresher for arithmetic for us, the range for this number would be 2,000 because 1,000, which is the maximum, minus 1,000 is 1,000 plus 1,000. When a negative and a negative meet, it becomes a positive, and the range becomes 2,000. So that's just a refresher for you. Basic math will help you in statistics. Okay, so look at the example here. When you have a range of numbers from 1 to 10, 1, 2, 2, 1, 4, 10, 8. The range is the maximum, which we believe is 10. 10 is greater than 8, and the minimum is 1. 1 is less than 2, and your range is 9. Okay, and but in practice, what's the importance of the range? Many people have argued that the range is not meaningful, and I'm going to show you that in the next slide. What we tend to do is report min max, and I really like that. You know, so if you came and said, well, let's imagine that Jeff Bezos, Mark Zuckerberg, and Elon Musk moved to Freetown, Sierra Leone, you know, and someone is saying, well, the GDP per capita in Freetown is doing fantastic, and someone else says, well, it's because of the outliers pulling the mean, and someone else will come up and say, let me give you a sense of the dispersion. The median is, I'm going to guess here that the median is 4. The median is 4, but the range is 9. And someone says, what does that mean? But say, okay, the min max is 1 and 10. And then you begin to understand, oh, wait, even though the median is important, when you look at the minimum and the maximum, you begin to understand how that number makes sense. Okay, below in this box, we have an example. Again, this is webinar style. I would have wanted to ask, does anyone know what?
Sorry, but before you go, I just want to say that please feel free to call people up if you want to. You know, I am happy to unmute them. I'll ask them to unmute and bring them up. That's one. Two is that we have a question to look where Amusa wants to ask a question.
Okay. Tell me.
You take it now?
Yes, sir.
Okay. So please ask your
question. On his behalf, if it's going to delay the asking.
So look, whether you want to ask your question? We can keep going. Okay, wait, okay. All right, go ahead. Ask your question, please.
No, I don't have a question. It was previous raised hand, sorry.
Okay, all right. Yeah, thank you very much.
All right. Okay, so look, since you are unmuted, you can unmute yourself. Do you know what the GHQ-12 questionnaire is?
No, sir.
Okay. Does anyone know? You can raise your hand. and I will wait 5 seconds before I tell you. And Tolu, you can stay unmuted. Oh, someone knows. Can we on Tolu stay unmuted?
Aisha.
The hot seats. Yeah, who's Aisha? Can you tell us? And Aisha, stay unmuted as well.
Good evening, ma'am. Good evening, ma'am.
Please go ahead, Aisha.
I think it's the general health question, yeah.
Okay, great. Okay. Let's move Aisha because of the static, and let's have Hassan on not the hot seat, on the nice seat. Let's call them the nice seat. And Temi Oladejo. Anyone who wants to volunteer, you guys will be my panelists. I will throw questions and then you can answer, and it would be, I promise you that it's better than if I am just going through the slides. Michael, I see Michael Essang, let's do that as well. Okay, who else is raising their hands? Okay, so Michael, do you have a question? Okay, yes, go ahead.
No, I wanted to say about the GHQ12 questionnaire.
Okay, tell me.
Yeah, it's a general health questionnaire.
We seem to have lost Michael. Okay, okay, so let me tell you what it is. We'll move to the next slide. I think I have enough people on the panel. If anyone else wants to join, Dr. Abioye, if there's connectivity issues, we can mute the person and then I'll just continue. And then I see OFMH has raised their hand, probably want to join the panel. Let's add them and then let's move on. Okay, so the reason why I've asked you this, right, is as we're learning statistics, you also want to learn or get insight to how the world of statistics and epidemiology and decision science and all of that operates. Now, some people have told us that it's a general health questionnaire, and a GHQ is correct. It's a general health questionnaire. When you go to the doctor says, "How are you doing today?" and you say, "I'm fine." And sometimes that is just a cultural response. "How are you?" "I'm fine," even if you were crying 2 minutes ago. And so people have decided that we're going to create what we call an instrument. An instrument really is a set of questions, and you can see that this is GHQ12. So it's 12 questions which ask you questions about your general health, such that your responses give an objective picture of how your general health is doing. So if you were to see a neurosurgeon, they would ask you questions about your brain in relation to life. But we want to capture questions relating to your general health. And so that's what it is. But the point to note here is that you can have a maximum score if you answer the GHQ of 36, and you have a minimum score of 12. So if someone were to ask you about the range, if someone got a score of 34, you know, and the minimum score was 18, and someone said, "What is the range?" and you said 16. What does that mean? It doesn't really mean much, because 16 could be 12 and 28, could be 14 as a minimum score and 30. You know, it could be 36 and 20. So that's why we typically use the mean max. So if you say the average score, when we ask people, when we administered the GHQ12 was 34, the minimum was 14, and the maximum was 36. Then we begin to understand how this data might look like without looking at a table. Okay, so let's move to the next slide. And I see that I'm almost at the half hour, so maybe I need to hurry this up. Okay, so now the next thing we want to talk about is percentiles. For those of you who are clinicians or who have worked in nutrition, you might understand percentiles better than most. So remember, so let me call Michael Essang. Oops, excuse me. Michael Essang, can you tell me what the interpretation of a median is? If Hassan Aderinola can get to her mic or his mic quicker, you can also answer the question. Okay, Tolu Amusa, can you answer that question? What's the interpretation of the median?
The interpretation of the median is the middle of the set of observation.
I like it. I like it. If you're talking to a lay person, that's a great explanation. Can you tell us a little bit, go a little more statistical and tell us? I see someone else raising their hand. Maybe they want to join the panel. OFMH, yeah, unmute yourself. Tell us a little bit. Go a little more hint. Use percentages to answer your question. Okay, OFMH.
I think when you talk about the median, it's the midpoint of a data set.
I like that, and that's what Amusan said as well. I see more hands.
Okay.
So
can I just add?
Add, yes, go ahead.
Yeah, so if you're using the percentage, like you said, the midpoint would be where you're going to find 50%.
Excellent. That is where I'm going to. Okay, so I want to say something real quick. When you learn epi and statistics, what people tend to do is they learn lesson 1 and they forget about it and they go happily to lesson 2. I don't know if this is how every other thing is taught. The clinical medicine is not necessarily taught like that, right? And so, however, epi and statistics, lesson 2 captures the essence of lesson 1. It brings into lesson 2 what you learned in lesson 1. And by lesson 4, you're supposed to bring in lesson 1, lesson 2, lesson 3, lesson 4. So we've said, and Tolu has told us that your median is the 50th percent. And let me add to that. It means that above the median, you have 50% greater than that value. And below the median, you have 50% less than that value. So let's think about this. When people say the median income, and I don't know why I'm using income today. The median income, household income in, I don't know, Kigali, Rwanda, is $45,000 per annum. Someone might say, oh, that is too small. But if you are an eternal optimist, you're going to say no to that. It means that 50% of the population are richer than 45,000. Many times we tend to look at, oh, 50% are poorer. It also means 50% are richer. Why have I spent all this time to tell you this? It's because when we're talking about percentiles, you begin to understand what a percentile means. So if they say that a child, for example, is in the top 10% of body weights in their class, MFOH, I'm sorry if that's not the, can you tell me what this means in terms of higher and lower than the point?
Please, the question again.
Yes, when they say that someone is in the top 10% of body weights in their class, what does it mean? Based
top
on
10,
what I just told you.
That means the person is above the 90th percent.
Exactly. So it means that 90% of the people are not as heavy as this child, and 10% of the people are heavier than this child. Bear that in mind. Okay, so stay unmuted, MFOH. You're going to be the one to talk about this slide. Okay, so when we're talking about 25th percentile, it means 75% is higher and 25% is lower. So this is also called the first quartile, Q1. This is going to become important when we talk about the interquartile range, and 50th percentile, Tolu Amusa told us, is the median, as you can see. The 75th percentile is in the third quartile. So when you do, and for those of you that are planning to do the GRE or have done the GRE, if you are in the 92nd quartile for quantitative, that means, and this is something that you need to know, it is not that you are 92%, you are better than 92% of the people who took your exam at the same time. The GRE is so stable that you are actually, if you get a 92 percentile result in verbal or quantitative, it means that you are 92%, you are better than 92% of everybody that has ever taken the GRE. So you can frame it and put it on your wall or put it in your resume after you take your GRE if your results. And if you are in the 10th percentile, that means that 90% of everybody in the world who has ever taken the GRE is better than you. Maybe you should also put that on your wall. That might be an achievement in reverse. Okay.
Someone said, can you please repeat the Rwanda illustration?
Okay, so the Rwanda illustration. Now let's talk about money again. Suppose I say that the median income in Rwanda, median personal income is $5,000. Somebody might say that means 50%, because Tolu told us that that's the 50% mark. 50% of the population earns less than $5,000. But the reality is also that 50% of the population is also richer than $5,000 per month. That's simply what I'm trying to get at. That a percentile is not necessarily what is lower, it also gives you what is higher. And so if somebody is at the 75th percentile, it means that 75% of the people are lower and 25% of the people are higher. That is the point that I'm trying to make. Okay, so the last point here is percentiles are also quantiles. I like this word. So you say 25th percentile, 0.25 quantile. So personally, I like when things are explained in lay people's terms. I like to keep things simple. Although people who listen to me talk say, no, Eboa, you use highfalutin language all the time. I don't know how to, what's the word, reconcile both of them, my personal and my personality. But however, I prefer percentile to quantile. Quantile sounds very grandiose. But anyway, the point is a percentile is a quantile if you don't express it as a percentage. So you say 25th percentile, but you say 0.25 quantile. People tend to understand percentages better than decimal points. The majority of people do not understand percentages at all. Because, for example, if I told you that if somebody comes to say, I mean, we're in a tech revolution in Africa, or so they say. So someone's going to tell you 100% revenue increase. And people don't understand that just means ×2. Did you know that, Tolu Amuson, that 100% increase just means ×2?
Yes.
You did? Excellent.
Yes.
Okay, so if someone says 100%, you will get 100% gains if you invest, and then you go and you invest 5 naira or $5. Well, 100% just means you're going to get $10. I'm not sure what you're going to do with that except buy a cheeseburger. Okay, let's move to the next. Yeah, I shouldn't dwell on percentages and quantiles. We are at the 30th minute mark and we have a poll. So I'm going to turn this over to Dr. Ibrahim. When I was taking this poll, I think I failed all of them, so maybe I'm not qualified to teach this class, but over to you, Ibrahim, and let's administer the poll.
So I don't have the poll set up in Zoom. Let's just have people respond?
Okay,
Yeah.
excellent.
Yeah, we can just ask people to say what they think.
Okay, so at this point, I'm going to ask for other people to volunteer to join the panel. And so raise your hands if you want to join the panel, and then we can retire some of the people currently on the panel and talk to new people. Do we have any new volunteers, or do we continue? Hassan, I've not heard your voice, and Michael, I'm not sure that, okay, we have one person. Okay, who else wants to volunteer? Nice. Okay, I see Ifedi Azie. I like that name. Sweet. Okay, so and I see Otunaya Tim Topekayode. I think that the more I see Ahmad and Musa. Let's start with Ahmad and Musa. What is your answer to this question? Oops, what's going on?
That's 300.
300, like the movie. Okay, who disagrees? Ifedi Ezie, do you agree? Do you disagree? Okay, you have to be quick if you're going to be on the panel. Let's try to hear from Temitope Otunaya Kayode. What is your answer? And Ifedi Ezie, if you're unmuted now, feel free to chime in. Let's go. What's your answer?
My answer is B also, 300.
300. Okay, I'm looking for disagreement. Who disagrees? Michael Esang. Hassan Adin. Oh, I'm so sorry. And I was born in Lagos, so shame on me. Hassan. Okay, it looks like everyone agrees. Let's see if the answer is correct.
Before you go, okay, yeah. So at this point, I think it might be a good idea to explain why 300 is.
Oh,
is
yes,
correct.
let's do that. So earlier I said I failed the questions. No, I did not fail the questions. I just said that to encourage us to see if they can beat my record. If you beat the teacher, then you're good, right? Okay, so in a trial to assess the efficacy and safety of ion supplementation versus placebo, even if I saw this question on a flight, you know, it just showed on my screen while I was in the air, I would know that this question was set up by Dr. Abioye. I don't know what his love for iron is, but among iron replete Tanzanian women, which of the following is closest to the range? So what they've shown you on the right is a distribution. So we're going to talk about a normal distribution and an abnormal distribution more, or maybe we talked about it last week. But you can see that, you can see somewhere here, can you see the cursor? I'm hovering over it. Dr. Ibrahim, can we see it?
Yes.
Okay, great. So somewhere here, around here, looks to be the maximum. And we can assume that this is an outlier, but also we can see here. Okay, Ifedi Ezi, get ready to answer a question. Remember, you have to be close to your mic. Why is the minimum 0?
And this is not a question about the biology, it's just from what you can see in the figure.
I mean, and you know, it's just a general overview. I want us to have an expansive mindset to this question. So this is a question on iron and iron deficiency. Okay, let's try Michael Esang. And I think someone else is raising their hand. Let's add them as well. Oh, I see a lovely name, Taye Bayode, Taye without the I. Taye, can you tell us why is the minimum for this 0?
Oh, hi there.
Yeah, talk to us.
Yeah, it's actually just a guess, though. I'm not really sure, but the minimum could be 0, maybe because the observation that was taken at that particular time, the value is 0.
I like your answer.
It could also be no. I think that's the answer, because if there is no observation, it could have been NA. So
I like it, but I don't agree with it. Sorry, I set you up. So I went to boarding school, and the house prefect would say,
then another guess.
Okay, tell me.
Yeah, then another guess could be maybe the trick, the way the histogram is actually being put into different bins, like just coming from the last lecture.
I like that too, but I'm not.
Still disagree.
Talk to me, ME.
Huh?
No, there's someone called ME who's raising their hand. What is the answer? Okay, once you're called on, unmute yourself and fire, talk, because we are time-based.
Oh, okay. Well, actually, I didn't go with the last person that said.
We can hear you clearly. Can you speak up, please?
Okay, I said I agree with the last person that speaks. It is not that the baseline iron level of the person is 0, but is the starting point of the clinical trial and also the distribution of the histogram.
Okay, great. So why the reason why I've asked this question, right? the hint is I want your thinking to be expansive. You are not learning epi and bio because it's an academic discipline. It's because it's for decision making. Epi and bio are the foundation of public or population health. And so it is, you are the population, you are the public, it is life. Okay, let me ask Tolu and Musan. Why? Because you raised your hand. Why is the minimum 0?
Yes. Yeah, in this graph or this histogram that we have here, we can see that there's a frequency on 0 and there's a frequency on the extreme that's 300. So I think that's why it's the minimum is 0.
No, not really. Okay, Tolu,
please, can I come in?
Who? Okay, fire down because we need to go.
I think that's the start dose.
That's the start dose. Okay, you are beginning. Someone, you are getting hotter. But let me move this forward. So who was the person who said that's the start dose? Was it OH?
Yeah, that's OF.
Okay, OF. Yes, OF. Okay, OF. Stay on the line. What is less than 0?
Minus.
Minus.
That is minus, yeah.
Okay, and this question is saying safety of iron supplementation. Which of the is closest to the range of baseline ferritin? So they are measuring the ferritin of the woman in this study. Can you go to a doctor and the doctor will say, oh, your ferritin is minus 20? Impossible. You can't have negative value of ferritin. That is why the minimum is 0. Does that make sense? This is what I'm saying. You have to think beyond your academic reasoning. It's like if someone shows you a graph and says, we're looking at income again, and someone's income is negative 200. Does that mean this person goes to work every day and at the end of the month he pays his boss 200? Why this is important is when you're looking at data, don't be too impressed with the data. Eyeball the data and check. Could there be a problem? If someone says their income is negative 200 and it's not possible that they pay their boss for showing up to work, you say maybe there is a mistake in the entering of this data. So we spent a lot of time just to show, and I hope you appreciate that when you are modeling data, that just because it is data does not mean it is correct. You have to cross-check and kick the tires. Now, another person will ask, is it possible to have 0 ferritin? If ferritin is necessary for life, is it possible to have 0? That is another question, but let's move on. Okay, so the interquartile range. Are there any questions or are we happy with this?
Yeah, I think we can keep moving on. There's a number of comments about, people are not clear why 0 is the minimum, but I get the sense that that's a debatable question, to be honest, and I don't think that that's going to be helpful to us to
Okay. So let's move on. If we have time, we can come to debate. I like to hear other ideas, but let's move on. So let's talk about, remember that we're still talking about measures of dispersion, and we've said the mean might be subject to outliers. The median may not be subject to outliers necessarily. However, the median may not tell you how this data is spread out. So we looked at the range to tell us how the data is spread out. Now we are looking at the interquartile range. So it's also a range. We looked at percentiles earlier before we went to the poll. And what we saw is that you can have the 25th percentile, you can have the 75th percentile, and you don't always want to say minimum, maximum. Let me go back to this graph that we were looking at. Okay, so you see that the mean is 0, the max is 300. Well, look at how far away the max is here from where the majority of the data is here. So even if you report the mean and max, it may not make a lot of sense because 300 is so far away from where the majority of the data is. what we begin to do, and you can see it here, what we begin to do is look at the interquartile range. The interquartile range looks at the 75th percentile versus the 25th percentile, but it does not subtract. It gives those values. So you're going to say the median is 30.4, the interquartile range is 19.1 to 49.6. And what this does is it helps you, it overcomes the limitations of the min max by giving you a sense of where the majority, maybe not the majority really, because it's 50% of the data, where 50% of the data lies. And that's what the interquartile range does for you. So let's, oops, where are we? Did we jump? I think we jumped a slide. Okay, so this is where we are. We'll go back to that. And okay, now let's talk about outliers. I really liked when I saw this slide. So shout out to Dr. Ibrahim for talking about outliers. Has anyone seen a box plot? I think we have a box plot.
That's next slide.
Somewhere here. Nice. So let's talk about outliers using the interquartile range and the box plot. So when you, I believe we've taught box plots before, right? I don't need to give a refresh.
No, we have not. This is the first
not.
time.
Oh, okay. Okay, let me tell you a funny story. So one of my friends was writing one of their papers for residency, you know, and he was telling me about how great his paper was, and he did all the box plots and histograms and blah blah blah, and he sounded very satisfied with his work. And frankly, I did not want to tell him that a box plot and a histogram are just the basics of presentation. But I can tell you, right, because you've not published a paper, and I don't want to talk about your paper. If you know what a histogram and a box plot are, I want you to understand that those are foundational, right? So, and the reason why I'm telling you this is because of why we're even doing this thing in the first place. And the reason why we're having STATS clinic is because we want clinicians from across the continent to play at higher levels. Okay, so that said, I've told you my why. I'm going to tell you the what about box plots. So a box plot is really the same thing. I wish I could draw this, but I don't trust my computer not to crash. A box plot is almost the same thing as this distribution, almost. It's the difference between this distribution here and a box plot is that this has real, you know, kind of this has numbers and frequency. But if you invert this box plot and make it horizontal, you're going to see that it may look very similar. Depends on how your eyes work. Anyway, let's go over a box plot. Now, ME, your hands are raised, so if you can unmute yourself, you can see that the middle line here is the median. So that's the first thing you understand in a box plot. The middle of the box is the median. The lower part of the box, and if this box plot was rotated 90 degrees, it would be the left side of the box is the 25th percentile. I wanted to ask someone to remind us what the median is, but let's move on. The top part of the box is the 75th percentile. So when you're talking about an interquartile range, you are going to say the median is maybe 5, the 25th percentile is 2, the 75th percentile is 7. So you're going to say 5 with an IQR of 2,7. And that gives us a sense of how packed or what the results of the data of the middle 50% is. And it gives you an idea of the spread of the middle 50%. Remember that your min max gives you the spread of the entire data set, but your median or your IQR gives you the spread of the 50%. Now, but we're going to talk about outliers. So after the box, you have the whiskers. So this whisker with this horizontal and this line is the upper whisker and this is the lower whisker. Again, remember that your box plot can be horizontal as well as vertical. So this would be the right end and this would be the left end. Okay, now, some people may assume that if you have any point on the whisker, it is an outlier, but that is not the case. In fact, some people might say if there are points outside of the upper whisker, it is an outlier. So let's go back to this. So you see here, someone might say 300 is an outlier because it's so far out, but that's not necessarily true. Because when we come to this slide, we can see that there is a formula for capturing outliers. It is 1.5 times the IQR below Q1, which is the 25th percentile, and an outlier is 1.5 above the IQR at Q3. So if, for example, your 75th percentile was 200, or let's say 250, you know, my math may not be so great. Then is 300 an outlier? Not necessarily, because 250 times 1.5 is greater than 300. So 300 may not be an outlier. So when you're looking at a histogram, you might say, this looks like an outlier. You should say, this looks like an outlier, not that this is an outlier. Because if you subject it to this formula, you may be wrong. Okay, so, and that is the point that is made here. The adjacent value is the lowest of, okay, I'm not going to do that. Let's move. I think we skipped this slide. Let's look at this. Oh, so this is exactly what I was saying. So maybe
question. I don't know if this person would want to speak up quick.
Okay, let's do a question.
Afiza Deladun, do you want to speak and ask a question? Please unmute yourself. I guess you can keep going. Okay.
So I see that we are 10 minutes before the hour, and but let's do a quick check. OF, yeah. OF, unmute yourself. How are you feeling so far? Give me one word, not one sentence. Give me one word. I want to test the range of your vocabulary. Let's go. OF, you're muted. Yeah.
Please, the question again. I didn't hear you.
I said we are almost at the hour. How are you feeling about this lecture so far in one word?
Oh, it's very interesting.
Okay, you gave me two. I'll take it. Let's go to Ifedi AC. Let's try if we can hear you. Unmute yourself. Give me one word, and then we'll move on.
Exciting.
What? Okay. You guys are making me blush with my dark skin. Okay, let's go for someone who's going to disagree. Taye Bayode. Unmute yourself, tell me. Okay, so silence means that maybe we're not doing a great job. So I'm going to quickly talk about this slide because we missed it, but I did mention something about it when I was talking about negative ferritin, positive ferritin, and this slide is basically saying look for extreme patterns that do not make sense. Remember when I said just because your data has been presented to you does not mean that your data is great. So for example, you know that a BMI, people say that a BMI of maybe, I don't know, is a BMI of 100 compatible with life? I don't know, I don't think so. If you look at this data here on the right. So you can see that we have 12 and we have 161. And then suddenly for this 100 person, we have 1,000. Suppose this was BMI, or suppose this was even blood sugar, or suppose this was high blood pressure, you know, And I know that you can't have a high blood pressure at 12. So just imagine with me. Instead of saying this is an outlier, wow, here's an outlier, what you would want to do is you want to ask and say, could this have been a mistake? Did the person want to write 98.7 but put 987? Did the person want to write 87? You know, and then if you can reach out to the person who collected the data, you find out. Other people will say, maybe you should not consider this data in your analysis. If this was BMI, for example, if you cannot get clarification from the person, I don't think it is statistical, I don't think it is biologically possible to have a BMI of 987. So you may want to drop this value. So the way I teach biostatistics, I say never drop observations. You can exclude them, but don't drop them. But sometimes if there's compelling evidence that this does not make any sense, a BMI of 1,000 is impossible, we've never seen it in the history of the world, then you might say we're going to exclude this value from the analysis. Okay, so, and we have it here. You see, that may have arisen from typos or mindless data entry. So someone like me who is very absent-minded, don't ask me to enter your data. Okay, so let's move on. We talked about the box plot, and we talked about how you capture outliers. So you can see here that it is called an outside value as opposed to an outlier, because what we have here on this slide is your calculation for outliers. An outside value on your box plot is not an outlier. Okay, so I find myself repeating things, and that may help you. If it doesn't help you, send a message to Ibrahim and say, that guy you brought to lecture us just keeps repeating himself. Let's do something about it. Okay, so here you are. It's the same thing. And let's look at let's move this from the definitions of what the parts of the boxes are.
We have a question.
Yeah, let's go.
Someone asks, when do you choose to use box plots?
Oh, that's a good question. So I'm going to deflect by saying, Dr. Ibrahim, let's hear your opinion, and please let's hear your opinion.
So sometimes if you look at the way the box plot is set up, you can see very clearly the outlier. You can see the distribution. So it shows data it shows the same kind of data that the histogram shows. Okay, but it also allows you to compare, and that's one of the things that you should see. I think the next slide shows comparisons, where if you look at the next slide, you'll see that sometimes it's best to have a side-by-side of two distributions. That's a perfect time to use a box plot.
Right.
Yeah. I mean, unlike a histogram where it becomes cumbersome to have two histograms side by side. The other thing is when, you know, the outlier is so clear, you can see that this is the outlier. The histogram might not really show you the outlier. I think Eboa had mentioned that earlier as well. Okay, I like it.
I'm going to summarize and say the same thing Dr. Ibrahim said by saying that sometimes you just want to keep it simple. If you remember that public health, and again, people may disagree. So I'm propagating this. Epi and bio at the foundation form public population health. Population health is decision-making for the people. The father of public health was called John Snow, and he broke a pump in London to prevent people from pumping water from that pump because the water in that pump was giving people cholera. The father of public health. Public health is interventions for the people. His name is John Snow, not the guy from Game of Thrones. There was a real doctor called John Snow. Now, if you present this to the governor of your city, of your state, and say, look at this, we need to do something, it's going to be like, who let this person into my office? But if you show them this box plot and say, oh, okay, you can see, or Your Excellency, you can see, this is the middle, this is the this is the upper boundary. The people over here, we need to do something about them. Even if he does not understand public health, he's going to say, oh, I get this. Anybody from here to here is safe. Anybody here is unsafe. And you say, yes, Oga. In fact, yes, Your Excellency. In fact, maybe we should look at the people from this adjacent line up to this place. From this upper part of the box, upper hinge upward, we are going to intervene. It will make things easier. And Dr. Abioye also said, when you put them side by side, look at this now. When you put them side by side, as long as your base, as long as your x-axis is not different across the box plot, now you can understand what is different. So if someone says the age of resident doctors in Lagos Hospital, and you want to say what is the median age, 50%, remember median is both 50 above and 50 below. Median age is 30. Let's assume this is 32, 31. Okay, right there it says 32.8 for female. And you can say it is closer to 34 or 35 for male. And you can have a comparison. Okay, so
can we take a break, maybe a 5-minute break, and then
let's do that.
Yeah,
let's do that. Okay, I'm going to pause and mute myself.
Okay, see you guys in 5. And 2, I see a lot of questions about doing box plots in Excel. Unfortunately, we will not be able to spend time to demonstrate to you how to do it, right? But if you check on YouTube, I'm sure you'll be able to figure out how to do box plots in Excel. The key thing will be, first of all, to have the data that you're going to use to play around with, and then take it from there. There's another question about identifying outliers in the box plot, and I have a board explain very quickly again before we go. But briefly, so there's not multiple lines. So you see the whiskers for the box plot. Oh, okay, a boy is here, right? So that upper adjacent value, the points above it, those are the outside values. Those are outliers. Okay. And yeah, that's 75th percentile, median, 25th percentile. Right. So it's the points that are beyond the lower adjacent value. Those are the outside values. Okay. And those are outside values are basically outliers.
Okay. And just to add on to that, sometimes some people would say, well, I don't want to agree that just because it's an upper adjacent value, it is, oh wait, Dr. Ibrahim, is this calculated or is this just your a diagram kind of thing?
So this is an example, but if you go to the ones where, not this one, like if you go to the next slide, yeah, no, right, the one on the right uses actual data.
So this adjacent value is that turnkey point, right? 1.5
yes.
Q3. Okay.
Yeah. So exactly. So that anything beyond that point is the outlier.
Is that okay? Great.
Yeah.
Great. So this is beyond. This is 1.5. Okay. Okay. Shall we continue or do we have a minute?
Yeah, I think we can get started.
Okay.
Sorry, I just want to confirm again.
Yeah.
We are saying that this line that is drawn, yes, that line is the upper adjacent value. And anything above that is an outlier.
Correct.
Okay, but then this value, this upper adjacent value, is it the one that we calculated with the 1.5 times
IQR?
Times IQR.
Yeah, plus the Q1. So basically, so if you calculate the IQR, the IQR, the 75th percentile minus the 25th percentile.
Yes.
Right. Whatever value that you get and you multiply that by 1.5.
Yes.
Then and add that to the 75th percentile, that gives you the upper adjacent value. So if you look at these numbers, it's roughly like the distance between the 25th percentile and 75th percentile. It gives you, I wish I could take over so I can point, like you can see that the whisker No, not this one. If you scroll back to where we just were. Right. So if you look at the whisker, you see that it's quite long, right? And if you add that to this one, then it gives you the what's it called, the outlier, the upper adjacent value. You don't quite get the same thing here for the lower adjacent value because the distribution of numbers just doesn't go beyond. Do you see what I'm saying?
Right. Okay.
Yeah.
Okay. So I didn't understand it this way prior. So if we go back here to this formula, you're saying that it is Q1 minus Q3 plus multiplied by 1.5 plus Q3 gives us the upper adjacent value.
Correct. Yeah.
Right.
So yeah, numbers above that.
Numbers above, that means, are we saying that numbers above these upper adjacent values are the outliers?
Yes, that's what we're saying.
Yes.
Okay, that means this formula here is, can we say this formula is
the formula for the lower adjacent value? That's the Q1 one. The one for the Q3 is for the upper adjacent value.
Okay.
Right.
Okay. This is good.
So I think Taye Bayode has a question. Let's take him quickly before we change gears and move to standard deviation.
There was someone talking just now.
Yeah.
Hello.
Yes, I just need to ask a quick question and just a comment as well, because you asked earlier if I was enjoying the program. Yeah. So I couldn't unmute myself, just to let you know that it's a high level lectures, which I'm really enjoying. Yeah. So the quick question is more like a clarity between calculating the outliers using the 1.5 times IQR and drawing the box plots. And my question would be from the angle of R, using R programming software. Basically, once I do my box plot in R, I think it's calculated, right? So I don't need to bother myself about this 1.5. So whatsoever I get from the R itself, once I see from the diagram, the observations that are just above the upper adjacent bar, automatically they're outliers.
Yes.
Just for more of clarity, and so that we don't really get mixed up with, do I need to sit down and start calculating 1.5 times this and this, or just go straight, do it with my statistical software, get the diagram, and know the observation that are outliers? You
are correct. Yes, okay. You don't need to make that calculation. There was someone who had started asking a question.
Thank you.
So let's have that person and then we move on. It was a female sounding voice.
I think we can keep going.
Okay, so let's move.
So one question, sorry. Someone said, why are we multiplying by 1.5? It is just a convention, right? There's a lot of things that we do that we don't necessarily have rules. It's just expected that by the time you get to that point, there's a general acceptance that you'll be far out enough in data that whoever is still out there is not part of the majority, is an outlier.
Okay. Well, thank you so much, Dr. Ibrahim. Let us move to standard deviations. Okay, so let's do a quick recap. Remember that when you have your measure of central tendency, it is not enough. Means are pulled by outliers, either to the right or to the left. Medians give you the 50%, but it does not tell you how the data is spread. So you need a measure of spread to help you with your mean and also with your medians. We looked at percentiles to make you understand what that spread should look like. We looked at box plots to help you understand the graphical or pictorial visual representation of spread. We looked at the IQR to give you the middle 50% of the data, and we looked at the mean max or the range, both the range and mean max, to give you a sense of how the spread happens. But when we go a little more technically, you want to capture not just not those simple, IQRs, although people are using the IQRs as a measure, but you also want to use the standard deviation. I'm going to try my best to explain this. So the standard deviation, lay speaking, is how far away a point on a distribution is from the center, from the mean. So let me quickly go back to this guy. This right skewed graph is actually very good, right? Okay, so let's imagine that this red line was the mean. It is the median, I believe, but let's imagine it was the mean. The standard deviation basically is saying, if we look at this point here where I'm hovering, how far away is it from this mean? Compared to this 300, how far away is it from this mean? Your standard deviation helps you say, you know how you say this person is 2 kilometers away from the locus point, which is the mean. And this other person is 10 kilometers from the locus point, which is, let's call that the mean. And so your standard deviation could be appears to be to the left. It could work to the left and also to the right. So let's go back to where we were. That's just in lay terms. But in addition to that, a small SD suggests that the data is clustered around the mean. So if you have a very tiny standard deviation, it means that a good part of your data is around the mean. But if you have a large SD, it shows that your data can be widely spread. And I just
excuse me, but is there a way to make your sound a little higher? People have asked, and I mean, I can hear clearly, but I just wonder if there is something you can do.
Let me wear a headset. Give me 1 second.
Okay, thank you.
How are we doing now?
Yeah, this is much better.
Okay. So yeah, I'm wearing this headset that I was thinking of throwing away because it makes my ears hot. Okay, so I was saying that, okay, Dr. Ibrahim, I want to ask you a question here. The SD for this normally distributed and this thing that may not be normally distributed, they would be roughly the same, yeah?
They could be, yes.
Because when we look at their mean and max,
so these ones are not likely to be because the values, we're looking at the same range of values, right?
Right.
And essentially we're looking at a group of, and we're looking at two plots that are both symmetrical.
That are both symmetrical, okay.
Right, so there's no skewing.
Mm-hmm.
You know, and if you look at the range, you'll see that one is narrow and the other is wide. So the one that is wide will have a larger standard deviation.
Right.
And the one that's narrow will have a smaller standard deviation.
Okay, so I'm asking this because we have 80 and 120 and 80 and 120 here. Anyway, let's go on. Let's go on. I wanted to make a point, but I wanted to be sure that I was correct. Okay, so let's move from this slide. And if I think to make the point, if it's important, then I will make the point. Now the next.
Sorry, before you go, someone asked, how do we know if a standard deviation is large or small?
Oh, nice. We're going to come to that when we talk about the standardized normal distribution. That's an excellent question, and we will take a look at it. But let's try to answer that, right? If your mean was what is the standard? Let's see. Let's try to calculate it. Let's look at the calculation for the standard deviation, and then maybe it will make sense. Maybe it will make sense to explain. Okay, so look at this. We're not going to go into the formula for standard deviation, but maybe I'll try to answer it when we look at this. So what you do with your standard deviation, what you do to calculate your standard deviation, you have a range of values. So in this case, we have 31, 38. Let's just look at it on this side. These are your ages. And what you do to calculate the standard deviation, the first step is you calculate the mean. And the mean here is X bar. So when you hear X bar, we're talking about the mean. It's 32.1. And the first step you do after calculating your mean is to subtract each individual value by the X bar. So you have 31 minus 32.1. Well, this value may not be correct, but let's just go with it. I think it's so you subtract the mean from each of these values, and then you square those values, and then you square those values, and then you add the total. And the next step to this, after you do this, is you divide that by n minus 1. N is the number of entries in the data set minus 1. So there are 10 entries in the data set minus 1, that's 9. And then you find a square root of that value, and you get 3.31. So the reason why we don't ask people, no one is asked to calculate the SD, it's not very useful, is because all your statistical softwares can do it. But we want you to get a sense of how it is done. So imagine that your mean, so to the question that was asked, imagine that your mean is 32.1 and your SD is 3.31. Just by eyeballing this data, you can say, you know, it is a small SD, especially because the SD is measured in the same SI unit as the mean. So you're going to say that the average age of doctors in Lagos Hospital, resident doctors, is 32. For this sample, let's imagine we could extrapolate this sample to all the doctors. You're going to say the average age of doctors in this sample is 32 plus or minus 3.3. And you see, you can say, just with your eyeball, you can say, oh, that's small. Why? Because your SD gives you a sense of how the data is distributed. So you can say, well, some people, a majority of people are 3 years older than 32.1, and a majority of, and many people are also 3 years younger. Remember that we said your SD goes to the right and also to the left. Just by using your eyeballs, you can get a sense of this data. Now we're going to get to how to look at SD and a normal data and a normal distribution, but that's where we are here. I want to say that the SD kind of gives you a sense of a margin of error, but that's not wrong. But if I did say it, maybe you will get a sense of what I'm saying. But let's hold on to that thought. Okay, now
someone has a question.
Yeah,
says, what is degree of freedom?
Oh, okay. So the degree of freedom, I really cannot tell you what the degree of freedom is, right? But it is a shall we say parameter or a variable used to calculate a lot of things in statistics. It's really, Dr. Ibrahim, can you explain degree of freedom in terms of how the data changes between each other?
So it just gives you a sense of, yeah, essentially it's based on a number of rules, and it gives you a sense of how the data changes. I think it's easier to see when we talk about like chi-square, right? You can see how the degrees of freedom is related to the number of groups that you're comparing,
right,
and all that. I wouldn't bother my head too much about it. I think the way to think about it is that it helps you to look in the table. Like if you're looking at a table where you want to figure out what the p-value is, right? Then you can, if you know how to calculate degrees of freedom for that test, and then you can use that to guide finding the p-value in the table.
Exactly.
I think that probably is sufficient for now.
Exactly. So a degree of freedom becomes very important when you're looking at a t-test or a chi-square. And if you're reading it from a t-table or chi-square table, yeah. So I think Dr. Ibrahim summarizes it very, very in as simply as you need it. It's really a statistical term that helps you calculate these things, but it is not necessary for how you interact with your statistics, except you were doing the science of the statistics. Okay, and that's why I skipped it. Okay, so let's look at this first. So we're talking about the standard deviation. When you have a normal distribution, we're going to talk about a normal distribution, but let's talk about the standard deviation and normal distribution. Remember when we said your interquartile range is the data observation at the 25th percentile and the observation at the 75th percentile, and then you can subtract or you can present that as the median and 25th and comma 75th. But when you have a normal distribution, and a normal distribution for now, let's call it a bell-shaped distribution. It's really a distribution that looks very symmetrical, like a bell. When it comes to the SD, you will find out that for every normal distribution, remember we also said that the SD is how the data is clustered, how far away it is from the mean. You will find out that to the left and to the right of the mean for a normal distribution, 68% of the data is captured within one SD. So remember, we're talking about measures of spread. So we have the IQR, we have the range, we have mean max, but we also have the SD. And the SD becomes important when your data is normal or when it is near normal. So 68% of your data is captured within one SD. And I say within one SD because it is from -1 to +1. 95% of your data is captured within 2 SD. That is from -2 to -3. And 99.7 of your data is captured between 3 SD of your data. And again, it's from negative to positive. Okay, and this is very important. And it is very important because it is used, the SD is used to identify whether data points belong to this data. So let me give you, and that's more used when we're talking about the standard error, and we're going to get there. But just imagine a data point. So these are all the points along the distribution. But just imagine that there was a data point here. This was 4 SD or 5 SD or 10 SD. You can easily say, come on, something that is so far away from the center, maybe it's an outlier, maybe it's an error, you know. And that's how you can think about an SD. But statistically, it's the SE, not the SD, but we're going to get there. I think we're going to touch on that just a little. Okay, so let's look at the normal distribution. So we've started talking about normal distribution. I've shown you what the SD does related to the normal distribution. So something about life is that a lot of things follow a normal distribution. And that is why it is very central to how we think in statistics. Okay, I'm also going to say the opposite of that, that even though a lot of things follow what we are going to call a near normal distribution, a lot of things also do not follow a normal distribution. Let us look again at my friend, this graph. You see this graph? This is your baseline serotonin. If you plot income, it's not going to have a normal distribution. It's going to have a right skew distribution. If you look at blood sugar, I think especially blood sugar basically in the general population, the people with ketosis are going to pull your graph kind of to the right. So a lot of things are also not normal. So don't go about saying, oh, this is not normal, we're not going to work with it. The importance of this point I've just made is that in statistics, many times we make assumptions about the normality. Even when it's not very normal, we can make assumptions and subject it to the to assumptions of being normal. And we're going to discuss why that is, one of the reasons that is, when we talk about the central limit theorem. Okay, so here's a point that I think needs to be made. If you receive data in, for example, let's see, kilograms to pounds, right? Or meters to centimeters. So if you multiply the mean by a constant, and this says e.g. 100, why? Because 100 centimeters make 1 meter, right? Centi is 100, so 100 centimeters make 1 meter. And if your mean was measured in meters, so you have 2 meters and you want to convert it to centimeters, you multiply by 100, you would do the same to your SD. So remember that your SD is the same SI unit as your mean. So if you say the age of doctors in Kigali Hospital is 32, the mean age of doctors in Kigali Hospital is 32, the SD is 3.2. It is the SD of 3.2 years. So if you convert that years to months for the mean, you should do that for the SD as well. If you add or subtract a constant from the mean, the SD stays the same. So suppose you say, if we, let's see, what is something that you subtract from the mean? Celsius to Fahrenheit? No, you also divide 2. But basically, if you remove a constant from the mean, the standard deviation does not change. So for example, just imagine that your bathroom scale adds five units to everyone that is measured on it. If you say we're going to subtract 5 from the mean, so that we capture everybody, and this might be a bad example, your SD, you don't subtract 5 from your SD. That's the point that is being made. Okay, so let's talk about, so this, remember when this person asked the question, how big or how small is an SD? And so I want to give you guys 1 minute to read these scenarios. So if we're looking at Nigeria, I don't know how much a bag of cement is, but imagine that your bag of cement moved from 5,000 naira to 5,100 naira. Is this a big jump? What if it's a diabetics blood sugar? It moved from 100 milligrams per DL to 200 milligrams per DL, and this is your not your fasting blood sugar, just your randomly measured. Would you be concerned? If your manager comes and says, we are going to make you senior manager in your company, and they move your salary from $40,000 to $40,100 per year, is this a huge jump? What if it's your mom's blood pressure used to be 95, now it's 195? Is this a huge jump? You see that 100, what does it mean to be 100 points different? We don't know. It depends on the situation. Okay, and so what we tend to do is standardize the normal distribution. When you standardize the normal distribution, you also standardize your SD. And then you can tell whether an SD is huge or whether your SD is small, and what's and how that makes sense. Okay, and basically, does someone have a question? Okay, and how do you standardize? You basically you calculate what you call a Z-score. When you calculate a Z-score, I hear baby, can we mute this person? Okay, what you do to calculate a Z-score is you take all the values in your data set. So look at this data set. If you remember this, guys, the age, and you subtract them from the means. You know, so what we did, the first step of what we did, you subtract them from the mean, and then you divide those values by your standard deviation. And that's going to give you your Z-score. You see, and because you divide that by your standard deviation, you're basically saying you're to use, for lack of a better term, you are standardizing your distribution. And your Z-score is how far away in standard deviation points are you from your mean. So now you don't have to say, is 100 unit difference a huge thing or is it a small thing? Your Z-score can tell you if it is huge or if it is small. So let me give you an example using our favorite variable, income. So if you say $1 million, that's huge, that's big, that's, oh my God, $1 million. But if you have a data set among millionaires and one person is $9 million rich and another person is $10 million rich, another person is $8.5 million rich, another person, you know, the difference of $1 million may not be statistically significant between those people. But we agree that $1 million is a lot of money. And so what you do is you want to convert your value, your distribution to a standardized normal distribution so that each point you can see how far away after you standardize them they are from the mean. And in nutrition, especially in nutrition, and Dr. Abiyoye will be able to tell you this, is that we tend to use a Z-score of maybe 2 or 3. For those of you who have worked on the DHS data set, you would see that a Z-score of 2 for nutrition, maybe for height for age or weight for age or weight for height, is considered to be either an outlier or is considered to be a cutoff, a threshold for how well a baby is doing. So they would say if the baby is 2 Z-scores below what we expect of the weight for height or weight for age, I don't remember those things, then we would say this child is malnourished. So they are not going to say, oh, the mean is 35 kilos, this baby is 20 kilos, so this child is malnourished. They use a standardized normal distribution. And that gives you a sense of how large or how small a difference is, or how large or how small a standard deviation is. If you have a very large standard deviation, then all your Z-scores will be small. If you have a very small standard deviation, then a difference, a huge difference, what am I saying? If you have if you have a large standard deviation, then a large difference from the mean would still fall closer to the mean than if you have a small standard deviation. Then a moderate difference from the mean may be perceived as an outlier compared to if you had a large standard deviation. Okay, so I don't know if you have questions on this, but let's try to move forward. And I think at this point, we're beginning to round up about measures of dispersion, but we want to be able to let you know that when you are talking, and let me track back and tell you this. Some people say that if you want to excel at anything, you have to excel at the lingo. You know, so if you, like we said, Africa is in a tech revolution. If you want to become a tech bro or a tech person or a tech sis, you have to learn the language, you know, and it applies across board. When you have a sample, and let me show you this again, our friend here, this is, let's call this a data set. It is a data set, but it is a sample. This you can't have only 10 residents in all of Lagos Hospital. You know, so you sampled only 10 people from the population of residents in Lagos Hospital. And again, note this, when people are talking about population, they're not talking about everybody in the country. A population may be specific. In this case, we may be talking about the population of resident doctors in Lagos, you know, versus the population of everybody in Lagos Hospital. So we have a sample of 10 from a population of resident doctors either in Lagos Hospital or a population of resident doctors all across Nigeria, if we assume that it is. Now, so let me start from the nomenclature, then I will go to this point, which is here about a population. Now, the population parameter is usually represented in, is it Greek or Latin? I think this is, are these Greek? Yes, it's Greek, right? So your population mean will be represented as mu, and your population standard deviation will be represented as sigma, but your sample measures, your sample estimates are measured in the Roman or the everyday alphabet. So you can see X bar is the mean of the sample, while SD is the standard deviation of the sample. Okay, this point is very important to note, that just because you calculate a mean of your sample does not necessarily mean it is the mean of the population. So let's come back to our nice data set that was here. So maybe someone will say, well, we did a study on resident doctors. We found that the average age is 32.1. And someone will say, foul. That is far from the truth as possible. The mean age of resident doctors is actually 40. And the reason why may be because either your sample is too small. I want to ask someone a question, but we're pushing it and we may be out of time. But someone might say, well, maybe because our sample is too small, maybe our mean falls out of the range of, there's some kind of systematic error and there's a 5% blah, 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 that makes us, that makes our value fall outside of the population mean. But the answer most times lies because of the way we sample data. And we may sample data based on a convenience sampling rather than a random sampling. So, and what does a convenience sampling mean? Suppose you're a resident doctor in Lagos Hospital, and you want to know the average age, and you go into your clinic and you ask all your doctor friends there, not the clinic, the cafeteria, all your doctor friends who graduated with you and say, tell me your age, tell me your age, tell me your age, tell me your age. And you capture those 10 people and then you want to extrapolate that. That's likely to be wrong. But if you do a random sampling and you say all doctors pass through these gates between 7 and 9, every 5 doctors that come in, I will ask them for their age. Then you might have a better chance at random sampling. And then your random sample estimate is more likely to capture the population mean than your convenience sample. Someone might say, okay, let's just go there and the first 10 doctors that come will capture that. Maybe doctors that are younger come in earlier than doctors that are older, because younger doctors don't have families and they are easier to come in. Older doctors have to drop their children at school. So you have to do random. The reason why I'm telling you the difference between random and convenience sample in relation to this sentence here, that the sample may not necessarily capture the population mean, is that in statistics, we mostly assume that your sample mean captures the population mean. We mostly assume, and that's based because we also assume that you've captured data randomly. So when you're doing a study, try to make sure you're capturing your data randomly so that your assumption that your mean estimate of your sample will be capturing or easily extrapolated to the population mean. And this brings us to this point that is made here. Excuse me. This point that is made here, which is when we run statistical analysis, we're not trying to understand what the age of the 10 people in Lagos Hospital is on average. We are trying to extrapolate that to the entire population. And this brings me to the point I was making, that we're not trying to say we're not asking for the age of doctors to extrapolate to the average age of all people in Nigeria. The population we are trying to extrapolate to is the population of resident doctors in Lagos, Lagos Hospital, or in Nigeria, or in Lagos or in Nigeria. Depends on how strong you can make this assumption. So remember that population does not just mean everybody, but it's context specific. Okay, now let us move to, based on that, we're going to move to the next slide to talk about your sample error. Okay, so I've laid a foundation, and please at this point, I'm going to say, if you have any questions, ask, because this is the foundation, or this is the basis for how you do statistical analysis. Now, the standard error. Okay, this is going to be a little tricky to explain. I might need help, but I also want to do it as quickly as I can. Let me take us back to our friend here. I really like this table, and so sorry if we're going back and forth. But let me explain something here. What we do in statistics, so look at this. We have 32.1 as our X bar. So you see, it's not mu, it's X bar. Remember, Roman numerals is your A, B, C, D, E. Your samples are represented as Roman numerals. Your populations as Greek alphabet. So we have our X bar, which is your mean, as 32.1. And we have our SD as 3.31. Remember that your SD talks about spread. It just talks about data spread, only data spread. Okay, great. Now, so we have these 10 people. We now want to extract, we've assumed that the person who collected this data did not ask 10 of his friends living in his building or in the cafeteria, but that they randomly collected this variable. So we are going to assume that the X bar is a very likely reflection of mu, which is the population. And we said it's not everybody in the country, but every resident in the hospital. Now, what we do in statistics, and your data software can do it. You can run the experiment yourself if you want to do it. If you take, so there's 10 people. I don't know if you guys understand what they call sampling with replacements. I'll quickly explain it. Okay, so so there are 10 people here, right? And these people have been randomly selected from the population. We assume that. Now, if you take 3 people by random here, so let's say we randomly take 31, 38, and 33, and we calculate the mean of those 3 people. Remember your mean, 31 plus 38 plus 33 divided by 3. And we write the mean somewhere. We put those 3 people back and we take another random. And this time we select 38, 36, and 29. We pull them out, we measure the mean, and we put them back into the sample. And we randomly take again 3 people. And again, by random, we select 31, 38, and 33, and we measure the mean, we write it somewhere, and we put it back. If we do this, statisticians tell us that if we do this 30 times or more, if we randomly select these people 30 times or more, when we plot all those means that we've been writing down after we take 3 people and sample with replacement. Remember, replacement is after you've selected them the first time, they are not disqualified. You put them in and they are still eligible to be sampled. What you are going to get when you plot all those means that you've written down on a graph is going to be a normal distribution. It's going to be a normal distribution. And that theorem is called the central limit theorem. So remember that I said everything, a lot of things in this world are normally distributed. But I said the reverse is also true. A lot of things in this world are not normally distributed. For example, income. For example, blood sugar of the general population. For example, height, I think. I don't know if height is normally distributed, but a lot of things are not normally distributed. So why do we subject our assumptions to whether a data is normally distributed or not? It is because of this central limit theorem that when we take, and you see it here, when we take several random samples 30 or more times, and we calculate the mean of each sample, the mean of those sample means is the, okay, before we get there, the distribution of those means, first of all, is normally distributed. And the mean of those sample means is the population mean. And this is how we know what the average blood pressure in Africa or in Nigeria or in Botswana is. We've never measured everybody's blood pressure. But when we take a randomly collected sample and then we continuously sample with replacement from that sample, the sample means of that sample will give us a distribution that's both normally distributed, and the mean of those means, and I know I'm confusing you, that's why I'm laughing, will be mu. That is the central limit theorem. And the last thing is that the standard deviation of that sampling distribution is called the standard error. Okay, I'm going to pause at this point. We're at 10 minutes to go. One person ask a question, and then we will move forward with the rest of this slide in 10 minutes. Anybody, nobody? Okay, so let's move forward. Okay.
Sorry, 1 second. I'm trying to bring people up to speak.
Okay.
Yeah, I was on mute myself. And Ganiat, I'm allowing you to speak. Please unmute yourself.
Thanks for the opportunity. Please, I don't understand the central limit.
Right. Okay. So, should I give it another go?
Yes, please.
Okay. Let me try. Let's see. Okay. So, oh yes, let me go back to our good friend. This guy, this is our good friend. Now, imagine, look at this distribution. This is not a normal distribution, right? This is a right skewed distribution. Now, what they're telling us here is no matter how your distribution looks like, if, for example, how many people are in this study? Let's say there were 200 women in this study, for example. Suppose I randomly pick 25 women out of these women, and I measure their iron ferritin, and I calculate the mean of those 25 women's iron ferritin, and I write it down one place. And I put those women back into the sample. And I collect another random 25 women. So this is called sampling with replacement. Just because a woman was randomly selected the first time does not mean she's disqualified from being selected the second time. If I did that, I would be sampling without replacement. But if I sample with replacement, I put them back into the sample, I collect another 25, I write out I measure their mean and I write it out. If I do that 30 or more times, when I plot their graph, their histogram of those means that I've collected from a repeated, maybe 35 times of 25 people, instead of it to look like this, it will look like this. It will be normally distributed and it will obey these laws of 68% of the data is captured, 95% and 99.7 is captured within 1, 2, and 3 standard deviations. Does that make sense?
And that is because they are being replaced, sampling with replacement, right?
Yes, and that is because data follows the central limit theorem. But for it to follow central limit theorem, you have to sample with replacement.
I understand now. Thank you.
Okay, sweet. Good. So not only do they obey these laws, the mean of your distribution will be the population mean. Remember when we talked about mu versus X bar? Not only will it be obey the laws, that center point will no longer be X bar, it will be mu. Now, but remember that I also said for it to actually be correct, let us assume that you have sampled your data without in fact, even if your data is collected and it's not exactly collected randomly, your center of that sampling distribution of the means will be mu. Your X bar will approximate your mu, will mostly approximate your mu when your data is collected randomly. And the last thing we said is that the SD of this sampling distribution is called your standard error. Okay, so let's move on. We have 7 minutes. So in reality, like we said, we've never calculated everybody's blood pressure in Freetown. So we cannot know what the mu is, but the central limit theorem gives us an estimate. The problem is when you look at it in Excel or in Stata or in R, when you take your sample, Stata would never say, oh, the mean of your population mean is different from your sample mean. It won't, even though it calculates an SE. Because we are assuming that your data was collected at random, so that's an issue. So make sure you cannot correct badly collected data by putting it into Stata or R. And that's what people are seeing with machine learning and AI. Machine learning and AI are as racist or as problematic as the people who are programming them. Garbage in, garbage out. But what we can do is, if we assume that your data is collected randomly and correctly, then we can assume that your X bar approximates your mu. Then your SE can tell us what level of confidence we have that your X bar approximates your mu. Who remembers 95? I wish we had more time. We would have gone over 95% confidence intervals and so on. But now, suppose you collect your sample, you can calculate your SE. Remember that your SE helps you estimate how likely your X bar approximates your mu. But how do we know the SE? The SE mathematically is computed from the SD by dividing your SD by your square root of n. So it's SD divided by the square root of n. So you see that in statistics, we are making a lot of assumptions. And Dr. Ibrahim, when you're talking about degrees of freedom and what's the other one, says these things are like convention. We assume that your data is collected randomly. And so we assume that not only does your X bar approximate your mu, Remember that X bar is sample and mu is population. But we also assume that your SE, the standard error of your sampling distribution of means, which is based on your central limit theorem, can be calculated from the SD of your sample. So this is supposed to be SD, not sigma, divided by, I hope I'm correct, divided by the square root of n. Okay, so here it is. So we're back to this data set. So your SD is 3.31, your suppose and your SE is 1.05. If we assume that X bar approximates mu, we can now calculate an upper and lower boundary. Remember, now we are tying this thing to dispersion. We are now saying, what is the likelihood that your mu falls between 32.1 plus or minus the standard error times, oh, that's another calculation by itself. So we don't go there. But we did in the last time, we talked about 95% confidence intervals.
And we will talk about that in next class. Next class, we'll introduce inferences, p-values, confidence intervals.
Excellent. Excellent, yeah. Excellent. And so this might be a good place to stop. You now say, now let me give you something more. Your standard error in layman's terms is called your margin of error. So if they say so and so is going to win the election by 3 points, 3 percentage points, and maybe I'm confusing you, so let's use milk. So you say if the average price of milk is $44, let's say $4, plus or minus 3. That plus or minus 3 is your margin of error. That means that we may be wrong. The population mean for a gallon of milk may be 4 minus 3, and this is just in lay terms, which might be $1, or it might be as high as 4 plus 3, which is $7. So the interpretation will be, and this again is lay term, you know, it's just, I'm just trying to give you an understanding. It's not exactly right. Your interpretation would be the population mean for the price of a carton of milk lies between $1 and $7. Your best estimation, your best guess is that $4 that you calculated in your sample. And at this point, I hope you've gotten a little sense of what it means to have measures of dispersion. And next time, you're going to learn how it is applied to statistical inference. The last thing, okay, so we're out of time, so I'm not going to ask. So the last thing I'm going to say is, you can see from this lecture that even I, who have been doing this for how many years, 7 years, and have a doctorate in something, a lot of these things, I'm like, oh, please, Dr. Ibrahim, help me. So you may not be able to get everything in one class, and you may not be able to get everything after 7 years. You may have to sit with people, but this introduces you to the entire concept. And the more you understand it, the more you are able to apply and be better at biostatistics and epidemiology. So I'm going to pause here. We can wrap this up, or if someone has a pressing question, I'm happy to stay back and answer your questions. So thank you very much.
Thank you very much. This is great. So if people have questions, we're happy to take them. Just raise your hand, and then we'll call you up. Otherwise, this has been a very engaging class, and has made it all worthwhile. Thank you.
Okay, thank you so much. It's been really a good class on my side. But then my question is, what is the criteria for determining the number of figures that are supposed to be in the subsamples for calculating the central limit theorem? Thank you.
Oh, that's a really good question. Thank you for asking. And Dr. Ibrahim, I'm happy to hear your thoughts. Let me tell you mine. My advisor told me that even if you do a sampling of 2, as long as you can calculate a mean, and as long as you can do it 30 times, you will get a what you call it. You will get the central limit theorem will be obeyed, and that's what I was told. And my advisor is a PhD in statistics from Ibrahim School, Harvard. So I believe her. But let's hear from Ibrahim as well.
So the issue is that statisticians do a lot of things to try to get around the limitations imposed by the data. So the reason why you can, if you resample 30 times, then you can estimate, do some estimation, and then the central limit theorem applies. I would say that as much as possible, you want to use a large enough sample in your data, not just because of the central limit theorem, but also because you want the data to actually capture the diversity of the information that you can get from the population. Yeah. This is what I'm saying. So if you think about, many of our societies are multicultural, multi-tribal, multi-ethnic. If you're going to say something about Nigeria, for instance, which has so many tribes, you want to make sure that as much as possible, you have as many tribes as possible represented. So you want a sample size that's sufficiently large. So maybe 30 might give you an impression of this, or might give you enough information for you to apply the central limit theorem. But is it truly believable? And that's one concept that we'll talk about next week. There's what the statistics allows you to do, but there's also what other people might be able to look at and say, do I believe that? Right? How about this? How about that? Did you capture this? Did you capture that? So that's always something to also bear in mind to make the statistics more applicable in real life.
Yeah, totally agree. Yeah. Does that answer your question? And does anyone else have another question?
It does. Actually, it answered very well. Thank you.
Thank you.
Right. I just want to a few quick announcements. So please check your emails on a fairly regular basis, as we're sending out things as often as we can. We've kickstarted R this past week. I think that we might have SPSS coming up soon. To check the schedules that we've emailed at the beginning of the class, and yeah, that the schedules will have information, and we will also send reminders. The Zoom links, right? So the Zoom links for the labs, we have not sent calendar invites like we did for this one. So you would have to look at the email that we sent with the Zoom links, because there's just so many labs, and people are able to choose, and we didn't want to go through the stress of choosing for you and compelling you, and then it doesn't work for your schedule. So for R, we have 3 sessions. You can attend any one that works for you. For SPSS, we have 2, and you can attend any one that works for you. I believe for SPSS, we have the first set of labs this coming Saturday. So looking forward to that. The homeworks that we sent last week are due next week, which is next Sunday. So if you have done the homework before you attended this class, you might find that some of the concepts were just explained now, and you might want to go back into your homework and try to redo it. So if you look at the homework that Google sends to you when you finish doing your homework, so Google, you might be able to click that link and edit what you submitted, right? And then make changes to whatever it is until you can make changes until the due date for the homework, which is the next Sunday. Okay. If you have any challenges, please reach out to us. We also send information about office hours. So basically, the way the office hours works is, if you think that there are important questions that cannot wait until the next class, which you would want us to address, you can if you go to the email that we sent about office hours, there's a link where you click and set an appointment to meet with one of us. Okay. I think we have about 4 or 5 hours of office hours each week where we're able to address questions, and you can sign up for 15 minutes of each class and ask your questions. We've already had a few people use the facility. We're looking forward to meeting with you. So that's office hours. If you have questions that are not addressed in class, or some other thing that you would want to talk about that's related to the class, that will be helpful to use. The only thing is that we do not tell you who you're going to meet because it depends on our individual schedules, which might change from week to week. So some people are complaining about not receiving our emails. Please email us if you're having issues with the email, and then we can check what's happening. Because this is a fairly large class, it's quite a bit challenging, like tracking down each person, you know, without you, like, first of all, sending an email. Like, there's so many people who have said in this Zoom comments that, oh, they're having issues, and it's going to be hard. So send an email to us if you're not receiving the links, if you're not receiving the emails. Send an email to us, and we'll check what's going on. Yeah, I guess that's it. So the SPSS links, again, somebody asked about that. The Zoom links for the labs, they're also in your email. If you haven't found it, please send an email to us so we can share that with you. But please look in your emails first, because as much as possible, it's best for all of us that we can save our time, you know, so we don't spend the whole day attending to emails. We can be able to spend more time on developing the course materials, okay, and making sure that we give you the best experience. Yeah, so the homeworks were sent by email. Someone said, which email can we send the complaints to? There's stats. Okay, we started using another email, but if whichever email you have is being attended to, so courses at starts.clinic or starts.clinic@gmail.com, either of those email addresses will work. And those are the same email addresses that we have been using to send out material. If it's a bulk email, it's easier for us to use the newer one, starts.clinic, than to use Gmail, because Gmail has been giving us some trouble. Okay, all right, I guess signing off. Thank you very much, everyone. Thank you very much, Ebua. This was a fantastic class.
Oh, thank you. Thank you, everybody.
Looking forward to meeting with all of you again next time.
Yeah.
Take care. Bye.